A very good afternoon to everyone who's present here. I'm Sanjana and
I'm Sharon.
okay guys, so today we'll be presenting on the topic of, give me a second guys. So we always prefer to take the normal route, right? But not many understand that it's like pretty boring. So today we are going to take like a small diversion and start off the day with a simple question which we have in store for you. Alright? So here it goes. This is the question. Can computers solve every problem? What do you all think? Like, let's say you all get a question for which you do not know the answer. What will you all do? You all might ask someone else maybe. If not, you will get out your phone or computer, type the question in and get the answer, right? That's how you all do. So in line with that, can computers solve every problem? What if I even say, if you give infinite amount of time and energy, even if you work with the cleverest set of programmers, even if you give infinite computing power, can still computers solve every problem? I need some audience feedback, guys. Come on, let me tell your answers. What do you think? Yes or no? Who says yes? Hands up. Who says yes? A small interaction, guys. Come on, don't be afraid. Who says yes? So everyone says no over here. Okay, who says no then? Everyone says no. Alright, that's pretty interesting, guys. Because the answer is actually no. So most of the questions can be solved by a computer. But there are certain questions which even a computer cannot answer. And if you ask me why, if you ask me to elaborate the answer, so if you don't mind, may I ask, like, can the business students come to your introductory computer science lectures and have a seat? Is it okay? Okay, so it's a bit busy, I guess. So that would be a hassle for sir, right? So what if I say that Charani and I have a very fairly short answer? We have the answer, short answer, which is no. Long answer is a hassle for sir. Therefore, we have a very fairly short answer, and that is, you simply sit back and follow the rest of our presentation to get to know about the Turing machine. Alright?
So let's first look into the object for the day. We'll be emphasizing on the following topics. Starting from the history, the importance, the formal definitions, the transitions, variations, combinations, and applications. So without wasting much time, let's get started.
Alright. Let's go back in time, guys. Years and years back. So in the early 19th century, there was this famous world-renowned mathematician called David Hilbert. Alright, so he challenged the world basically. He challenged the mathematics community with a series of problems. And one such problem is called the Einstein's problem, as you see over here. What is it called? The Einstein's problem. So it's in German, guys. So for convenience sake, it was given in an English term, the decision problem. What exactly is this decision problem? Let's look into it. So this is the definition. Is there an effective procedure for deciding if a given statement is provable or non-provable given all the axioms of math? Feeling complicated? The definition? Okay, I'll explain to you in very simple terms. So this is what we are trying to say. Like for every mathematical statement, is there like a step-by-step method which we can follow in order to find whether that statement is true or false? Simple as that. Okay? So Hilbert went on to give an answer saying yes. So this man, Hilbert, he was an optimist. So he thought for every question, an answer could be given in a step-by-step method. Alright? And this is where the hero of our story comes into play. None other than Alan Turing himself. So this Alan Turing, he got intensely interested in finding an answer to the Einstein's problem, a solution to this Einstein's problem. Now this Turing, he is not just an ordinary man, guys. He is a bit beyond the ordinary people. Because you know what happened? He noticed a slight issue with Hilbert's question. That means this man Turing, he found a problem in the problem itself. See how brainy he is. He found a problem in the problem itself. Alright. So let's see what's this slight issue. So here we have the Einstein's problem. Alright. As you can see over here, okay, the world-renowned mathematician, who is that? David Hilbert, he failed to give a definition for this effective procedure. Alright. Actually, effective procedure in today's context, it refers to the term algorithm. What is an algorithm? It's like a method to solve a problem in a finite number of steps. Okay? So this algorithm is something very fundamental to how computers work. But back in the 90s, at that time, the concept of algorithm was like very vague. Even the computers which we use right now, they weren't there back at that time. Okay? Let's see whether you all know this fact. This is like simple, did you know fact? Okay? Let's see whether you all know this. Okay. So after the 1940s only, the first ever electronic digital computer was invented. Alright? But before 1940s itself, the term computer had been in use. How is that possible? Don't you feel illogical that like computers weren't in existence, but the word computer had been in existence? How is that possible? That means they have referred to something else by the term computer. And what is that something else? As you see over here, before 1940s, what did they refer to the term computer? It's an occupation. It's a job, guys. Like how we have doctors who do treatments, like how we have lawyers who argue and deal with legal issues. We have had a set of people called human computers. And what did they do? They performed calculations based on a set of instructions. Alright? Now, let's assume, just for some understanding, let's assume that my friend Chalani over here, in her last birth, okay, in her previous birth, she was a human computer. Okay? So now I'm going to ask Chalani as to how she did her work back in the 1940s as a human computer. Okay? Chalani, go ahead.
First, I'll read the table of instructions. Based on these instructions, I will write the symbols on a piece of paper. And in case I make a mistake, I will erase the symbols and replace it with a new set of symbols. And like this, once my computation is over, I'll stop.
Okay. So this process of a human computer, so Shalini is our human computer. This process of a human computer was not looked into by Turing himself. And he got really fascinated. Because why? He recognized that every step of what Chalani as a human computer could do can now be automized into a simple theoretical machine. So this whole block over here, as you can see, this is considered as the revolutionary part in the history of computer science. Okay? So, how did Turing convert the human computer's process into this simple theoretical machine? Let's see how it is. So instead of the human element, instead of my friend Shalini, we have the read or write head. That is this part. Alright? Instead of the piece of paper on which she wrote the symbols, okay, we have this infinitely long piece of clay which is divided into cells. So this is how everything that can be done by a human computer like Chalani can now be done by the simple theoretical machine. And this machine is considered to be the famous Turing machine. And moreover, in addition to that, this Turing machine is considered as the definition, Turing's definition for effective procedure. Now you all remember what effective procedure is? Effective procedure. So that was the problem, and don't you all remember that was the word that Hilbert failed to define in the Einstein's problem. So over here, Turing, he gave the definition for this effective procedure. And with that, now the question is complete, right? Question is very well defined. So what would have been Turing's answer for this problem? He went on to find an answer for this problem, but he found a small issue in a word, effective procedure. Now he basically defined it as the Turing machine. So what would have been his answer? Hilbert said it's a yes, that we can find answers for the problem, like based on a set of methods, right? That's what he said. But Turing, he said it's a definite no. As you see over here, it's like a complete contradiction to what Hilbert said. And how did he say this basically? This was not told based on his institution, right? He proved it logically based on evidence, and that concept is referred to as the halting problem. So like we have the clash of clans, here we have the clash of mathematicians and the mathematical world heating up gradually. Okay. So ultimately, Hilbert's program ended up in complete failure, and Turing was the person who contributed to identify the mistake in Hilbert's question. And he also proved that this leading mathematician, who is it? Hilbert's, his view of mathematics is completely wrong. Okay. Now we have this word, computer science. It's like a buzzing word in this modern era, right? So what does it actually mean? It is a study of what computers can do and can't do. Now until this point, even you all would have thought that computers are like this amazing machine which can solve any problem which is given to it, right? You all would have thought that. But actually, even before the first electronic digital computer was invented, Alan, he worked on to find that computers do still have limits in computation. Alright, that's why we say Turing's work is said to be the essence of computers, which gave birth to the entire field of computer science. Because why? We talk about what computers can do and can't do, and Turing machine exactly proves them. And that's why we now call Alan Turing as the father of computer science itself. Now let's go back to that previous question which I asked. Can computers solve every problem? The answer is a definite no. And now you guys know the reason behind that. Why? Because Turing proved using Turing machines that there's something called halting problem which makes computers to not solve certain problems. Alright, so the answer comes as a no. So in order to get a more clear understanding as to how Turing machines work, we'll do a very simple activity over here, and we need a volunteer from the audience in order to perform that activity. Who would like to come up? Anyone? Any volunteers? Keshavi, would you like to come up? Yes, please. Convert these ones to zeros and zeros to ones. But you shouldn't think of your own end, okay? We will give a base set of instructions. You need to follow the instructions. That's it. Okay? Just follow the instructions. That will be perfect. Okay? So you go and stand in that zero. Alright. You guys have to help her because she might not be able to read the table of instructions. So at what point is she right now? What is the symbol you are currently reading? Zero. Right. So since she is in zero, now she has to erase the zero and write 1. Alright. As she has written 1 now, she has to move to the left. To your left. This way, this way. You turn. You look at the Turing machine. Okay, very good. She has come to the left now. Okay.
Now, occasionally, what symbol are you standing at? 1. Now, what are you supposed to do? Now, when the symbol is 1, we have to write the opposite, which is a 0. So, and then you have to move to the left. Okay, now you have to convert the 1 into 0.
Okay. And move to the left again, right?
Now it says a blank symbol. So when it is a blank symbol, the operation ends there. So
yeah. As you see over here, when she's in a blank symbol, she doesn't need to write anything, and she doesn't need to move also. Therefore, the operation ends over there. Okay. Well done. Thank you. This is basically how a Turing machine works, guys. As simple as that.
a graphical illustration of a tape which we use for our activity. Then you have the read-write head. So in our activity, occasionally will play the role of a read-write head. The table of instructions, you must have seen it in the previous slide. And the states and the transition functions, I will explain it to you in another few minutes. So, as you all know by now, a Turing machine consists of an infinitely long tape on which read and write operations can be performed. This tape is then divided into cells, which is also in infinite amounts, each of which can hold a certain symbol. So, these symbols are also called as the alphabet of the Turing machine. There's also another special pointer called the read-write head, positioned on one cell at a time. So this is capable of moving as well, and is also capable of reading and writing new symbols into the cell. So in our activity, did you guys notice how Keshani performed the operations? First, she was asked to read the table of instructions, and by that, she was first asked to read the symbols on the cells, and then she was asked to edit the symbols by changing the zeros into ones and the ones into zeros. And she also moved throughout the activity from the left to the right. So these are exactly the three operations that are pointable that the head would perform. That is to read one symbol at a time, to edit one symbol that is the right or to the left, and also to move to either to the left or to the right.
One second, Charlie. So guys, you can start studying for the in the exam now itself. So what are the basic three operations over here of a read and write head? What did she do first, Keshali? She read the symbol, right? Okay, read, that's the first thing. Second one, edit, she erased and wrote another symbol. That's correct. Then the third one, she moved. Simple as that again.
And now we can move on to the alphabet. An alphabet refers to a set of symbols that the machine can write to and read from each one of these cells. The alphabet is denoted by the letter sigma, and it includes any finite set of symbols including letters, digits, and even special characters. Here in our case we use zeros and ones as the alphabet. And in some cases this alphabet might also include a special blank symbol which represents an empty space or an empty cell. This diagram too consists of such empty cells. And also a special point to note here is that the set of symbols included in this alphabet is actually determined by the design of this Turing machine. So it totally depends on the level of task you use to perform by this Turing machine. Okay. So now we can talk about the states. So what is a state? A state refers to the specific internal configuration of the machine that represents its current mode of behavior during its operations. The state determines the machine's control, or it can even influence the machine's decision-making process. Typically, there are three types of states. We have the start or the initial state, the accepting state, and the rejecting state. The start state is what you see first when you initialize this Turing machine. It's simple as that. The accepting state is where the Turing machine enters right after it successfully processes its given input. In other words, like the input written onto the tape, if the input written onto the tape satisfies the criteria defined by this Turing machine, then it will reach this accepting state. So to make you understand this, let me tell an example. So if a Turing machine is asked, if a Turing machine's job is actually to determine if a number is even, it would reach this accepting state only if it identifies that the given input is an even number. In opposed to that, when the input has not been accepted by this machine, it will reach a rejecting state.
So if the input symbol was an odd number, it would have reached the rejecting state, right?
Exactly. So that is because the Turing machine was only designed to accept even numbers, not anything other than that. So
3 points to remember here as well, guys. Accepting the start state, accepting state, and the rejecting state. 3 states. Okay.
So then transition. A transition is a key component that determines the behavior of a Turing machine. It specifies the rules on how the machine should behave when it encounters a particular symbol on the tape while in particular state. So, each transition rule is defined by a triplet called the Q, S, and P. The Q represents the current state, S represents the symbol being read, and P represents the action to be taken. And all these components together determines the Turing machine's next state, the symbol that should be written on, and also the movement of the tape head, that is whether it goes to the left or the right. And in general, a transition function takes the current state of a system as an input as its parameter and returns a new state that the system should transition to. It can be thought of as a set of rules that dictate how a machine should behave over time. System should behave over time. Overall, the combination and arrangement of these states along with the transitions between them determine the behavior and outcome of a Turing machine's computation. To make it simple, what this means is both this transition function and the state, they are actually working in line with each other. So together, this is what controls the behavior and the outcome of this Turing machine. That is why they are called the key components of a Turing machine. So hope that was clear to you.
Key components of a Turing machine. What are the two?
We have the transition function and the states. They work together to determine to control these behavior and outcomes. And now, putting all the technical aspects we learned so far, let's try to understand this formal definition. So this formal definition is in terms of 7 tuple. And why do I say it's a 7 tuple? It's because we have 7 letters inside this tuple. And each one of these letters denotes a very technical term which we have learned already. So let's look into each letter. First we have the letter Q, representing the set of states that the machine can be in. Then letter sigma, representing the set of symbols, input symbols that the machine can read from the input tape. So this includes letters, digits, special characters, and even blank symbols like I explained before. Here we have the ones and zeros in the activity. And this is letter gamma, representing the tape symbols. So the tape symbols are similar to the input alphabet which we talked about in the previous slide. And now this is the transition function. This represents the transition function which was called the del, the sign del. Then the Q naught representing the starting or the initial state. Letter B for the blank symbol, the blank cell, and finally letter F for the accepting and rejecting states. So here the accepting and rejecting states together are called the final states. Now finally we can talk about the variations of a Turing machine. So variations in other words means the main types of a Turing machine. First we have the multi-tape Turing machine. So this is similar to any other ordinary Turing machine except that it has multiple tapes with its own tape head. And each tape can perform read and write operations independently from each other. And the advantage here is that these multiple tapes can be used to store different types of data. And also they allow you to perform multiple computations simultaneously. And then we have the non-deterministic Turing machine. So this too is similar to this ordinary Turing machine. But however, this has the ability to choose which path to follow based on a set of non-deterministic rules. So instead of following a single predetermined path, exploring all the possibilities in parallel. So this too can lead you to make faster computations due to its high flexibility, and also useful to analyze the complexity of algorithms and problem solving. And the final one, we have the universal Turing machine, which is the most important out of all. A universal Turing machine can simulate any other Turing machine. In other words, it is able to read the description of another Turing machine on its tape using its tape, and then simulate the behavior of that machine using its own transition rules and internal states. This concept was the 1930s, and the importance of this is that it provides a theoretical foundation to the notion of algorithmic computation, which we talk about these days a lot. So with that, my part of the presentation is over, and now I hand this over to Anjana to talk about the advanced topics under this subject.
So guys, as I said before, this Turing's work is considered to be the essence of computation. Why? Because it gave birth to the entire field of computer science. What was computer science? You all still remember? It's a study of what computers can do and can't do, right? So basically, Turing proved that using the Turing machine. Therefore, this Turing machine is like linked and connected to diverse advanced topics. And one such topic is Turing complete. So Turing complete is basically if a computational system or a programming language, if it can perform any computation that can be done by a Turing machine, then it's called Turing complete. So for example, we have these languages like Java, Pascal, C++. They are called Turing complete. Alright? Then if we go on to talk about the computability aspect, okay? If there's a problem that can be solved by an algorithm, then it's set to, it can be also solved by a Turing machine. Therefore, if a problem cannot be solved by a Turing machine, then it's considered to be a non-computable problem. And this is given like a specific term. What is the specific term for non-computable problems? We say undecidable problems. That means it cannot be computed using an algorithm. So these are the examples we have for undecidable problems. So first one is halting problem, which is like Turing's development. Over here we have post-correspondence problem and Lagrangian equation. So basically these are the examples for undecidable problems. Alright? Then after this we have topics such as the computational parts of Turing machine, the process, the applications, the Church-Turing thesis, then the halting problem, which is like considered the core of Turing machine work. But unfortunately, our fellow partner, our fellow member Anjali, she couldn't be present here today as she is under medical leave. Therefore, we will not be covering that part. But I hope that we can get a recording from her, right?
Sure.
Okay. If we can get a recording from her, we will share to you guys, and I hope that you guys will not be lost for the end examination. We will make sure that you all are back in track for the end exam, okay? By making sure to get a recording from her part. So these are her parts actually. So before concluding the presentation, I would just like to clarify a small matter, okay? Let me ask this simple question again. So how big do you think this Turing machine is? Like a size? I'll give you three options, okay? Do you all think it's this size? Okay? Do you all think it's from here to here? Or do you all think it will like consume this entire room space? 1, 2 or 3? Just shout it out. Anyone? 1. Okay. Others? 1. Since Mihan said 1, everybody is saying 1 now. Is it? Guys? 3. Okay. 1 and 3. Others, come on. 2. Okay. We have all the possibilities now. Sample space is 1, 2 and 3. Okay. I'll tell the answer now. Actually, Turing machine is not a physical machine, guys. It's not like a washing machine you can touch and feel and deal with. It's actually an abstract model. It's like a mathematical model which Turing developed in his brain, and he wrote it in a paper so that the people would know. It is not a physical machine which was like implemented and it doesn't have parts and all. Alright, it's just written on a piece of paper. That's it. Alright. So even though being like theoretical aspect, even though being this simple, it has gone so far into the field of computer science that and decides what computers can do and can't do, right? So that's how important is this concept is. Alright? So do you all feel how weightage we have to give for this concept? Yeah? Yes. Alright then.
So with this, our presentation comes to an end. So hope you got something valuable out of this, and thank you all for your time and